In this video session, we will be talking about positive definite matrices and symmetric matrices. Let's start with symmetric matrices. What type of a matrix do you call as a symmetric matrix? A matrix A whose transpose will yield back matrix A. So in equation you can write it as A equals A transpose. In symmetric matrix, we will be mainly learning about their eigenvalues and eigenvectors. So first point deals with eigenvalues of symmetric matrix. Eigenvalues of any given symmetric matrix is always real. They are real valued. Okay. The next point is about eigenvectors. And for any given symmetric matrix A, the eigenvectors are perpendicular to each other, or in other words, you could tell they are orthogonal to each other. The simple example of a symmetric matrix would be identity matrix. So let's write down a 2 cross 2 identity matrix. What are the eigenvalues for this identity matrix? They are ones. Yes, they are not unique. They are just ones. What about eigenvectors? Any vector can be eigenvector for identity matrix. But any two vectors need not be perpendicular, right? So what we mean by eigenvectors are perpendicular for symmetric matrix means we can choose the eigenvectors such that they are perpendicular. For a 2 cross 2 identity matrix, you will get to choose vectors from the plane, and you can choose two vectors such that they are perpendicular to each other. Now let's try to understand, are eigenvalues always real? We have a small proof for that. We will start with the proof with the simple equation we all already know, that is Ax equals lambda x. Lambda is your eigenvalue, which is a scalar. X is your eigenvector corresponding to that eigenvalue. Let's start this proof by assuming that your lambda is a complex value. So lambda 1, let's say it is a plus ib. One important point to note is, whenever eigenvalues are complex, they always occur in complex conjugate pair. So there will be some lambda k such that it is a minus ib, which you can represent as lambda bar. So let's do that. We will assume the lambda is complex. So you can write one more equation saying ax bar equals lambda bar x bar. Now here x bar is the vector corresponding to lambda bar. Let's now take transpose of this. We already know AB transpose will yield B transpose A transpose. So here we get x bar transpose A transpose. I'm sorry about that. A transpose equals lambda bar is a scalar value and scalar transpose remains unchanged. So you can write it like this. Now let's multiply x bar transpose for first equation on left hand side. So you get x bar transpose ax equals lambda is a scalar value, x bar transpose x. Now on the second equation, we are assuming A is a symmetric matrix. So what can you do about A transpose? A transpose becomes just A because it is a symmetric matrix. Now, to make the left hand side of second equation same as left hand side of first equation, we will multiply by x on the right side. X bar transpose A x will give you lambda bar x bar transpose x. So you can observe for both the equations left hand side is same. So you can now actually equate both the right hand sides. What does this in turn mean? Since these two are same, it means lambda equals lambda bar, which is possible only if they are real values, not if they are complex values. Okay, now let's move on to the diagonal equation. We have already seen the diagonal equation, right? A equals, sorry about that, A equals, yes, capital lambda S inverse. So what does S stand for? It stands for matrix of eigenvectors. Lambda, capital lambda stands for matrix of eigenvalues, that is a diagonal matrix, and S inverse. We have seen eigenvectors are perpendicular. A perpendicular vector can be made orthonormal by dividing with its own magnitude. A matrix of orthonormal vectors is called orthogonal vectors, right? So you are basically converting this S matrix to orthogonal matrix by making those eigenvectors as orthonormal vectors, and orthogonal matrix is represented as Q, and this is only for symmetric matrix E. Okay, so lambda remains as it is, Q inverse. We have also seen one more important property of orthogonal matrix, that is you can get your Q inverse simply by transposing that matrix. So this becomes easier, right? So you get Q transpose. So this equation is known as spectral theorem in mathematics. Is known as spectral theorem. Now one more important point which we can note down, especially when you have matrix of large size. Let's say you have a matrix A which is of size 50 cross 50, right? 50 rows and 50 columns. If you are using pen and paper to calculate eigenvalues, it is a very tedious task. Comparatively, calculating pivots is okay. So what can you get some relation between pivots and eigenvalues? Let's say you found out the pivots and 20 of those pivots are positive sign, 30 of the pivots are negative sign. You cannot directly tell about the eigenvalues, but you can definitely infer eigenvalues signs. That is, if you have 50 eigenvalues, 20 of the eigenvalues will be of positive sign, 30 of the eigenvalues will be of negative sign. Let me remind you, pivots and eigenvalues are not equal. The number of positive pivots will be equal to number of positive eigenvalues. Okay. Now let's take a small example to see for ourselves, compute and see that eigenvalues are real and eigenvectors are perpendicular. Okay, let's start. Let's take a simple matrix A equals 1, 2, 2, 4. Start with computing eigenvalues. You use characteristic equation, that is determinant of A minus lambda I should be equal to 0. So the determinant of A minus lambda I am writing the equation directly. 1 minus lambda into 4 minus lambda minus 4 equal to 0. This in the quadratic format you get lambda square minus 5 lambda plus 0 equals 0. If you calculate this, you will end up with 2 lambda, that is 0 and 5. Okay, so you can observe here lambda 1 and lambda 2 both are real. So first point we have observed. The second point deals with eigenvectors. So let's calculate for eigenvectors. So let's take first when lambda 1 is 0. 1 minus lambda, that's 1, 2, 2, 4 minus lambda is 4. You are basically finding the null space here. So what is the row operation you do? R2 equals R2 minus 2R1, right? So your matrix gets reduced to 1, 2, 0, 0, x, 0. Here the free variable is set to 1, and if you compute using back substitution, what do you get? Minus 2. Let's call this as q1 vector corresponding to eigenvalue lambda 1. Now let's quickly calculate for lambda 2, that is 5. What do you get? The matrix changes to 1 minus 5, that's minus 4, 2, 2, 4 minus 5, that's minus 1. So x should yield 0. What is the row operation? R2 equals 2R2 plus R1. So your matrix has become minus 4, 2, 0, 0, and x should yield 0. Here again you are going to set your free variable as 1. If you compute, you get half. You can multiply it by 2 to get 1, 2. You are removing the fraction. Okay, we will call this as q2. What is it that we have to observe for eigenvectors? That they are perpendicular to each other. So we have q1, which is minus 2, 1, sorry about that, and we have q2, which is 1, 2. To prove two vectors are perpendicular, which equation do you use? q1 transpose q2 is equal to 0. So let's try it out. Minus 2, 1, 1, 2. So you are getting minus 2 plus 2, that's 0. So we have successfully observed eigenvalues are real, eigenvectors are perpendicular to each other. Now this much background is sufficient to understand the next concept of positive definite matrices, right? So let me clear this quickly. Let's move on to positive definite matrices. Positive definite matrices are symmetric matrices along with a few more properties. So not any matrix can become positive definite. They have to be symmetric matrix first. Okay, now let's try to understand the other properties which makes a symmetric matrix as a positive definite. Okay, so the first point would be all eigenvalues should be greater than 0. Yes, and all pivots. What can you conclude for the pivots? We have already seen number of positive eigenvalues and number of positive pivots will be same. So if all eigenvalues are greater than 0 means they are positive. So pivots also will be positive. So all pivots have to be greater than 0. The last part is all subdeterminants should be greater than 0. I will explain you what is subdeterminant soon. So let's take a small example of a 2 cross 2 matrix A, B, B and C. You can observe it's a symmetric matrix. So what does the first point say? The lambda 1 and lambda 2 has to be greater than 0. What about the second point? The pivots, right? So this will be your first pivot. So A should be greater than 0. Your second pivot will be AC minus B square by A, which has to be greater than 0. The third point is about determinants. So this was your first point, this was your second point. The third point is about determinants. Subdeterminants means 1 cross 1 determinant, 2 cross 2 determinant, 3 cross 3 till n cross n. Okay, so your first subdeterminant will be this 1 cross 1 should be greater than 0. What is your second determinant? It is 2 cross 2 AC minus B square, which also has to be greater than 0. Let's take a simple example to understand this now. So let's take a matrix A. What value shall we give for matrix A? Let's take 2, 4, 4 and 10. So what was the first point? The lambda values are greater than 0. So let's compute the lambda. Using the characteristic equation, I will write the equation here. 2 minus lambda into 10 minus lambda minus 16 has to give a 0. So if you write this properly in a quadratic form, it is lambda square minus 12 lambda plus 4 equals 0. So you can see using factorization method is a bit difficult. We will use the formula. What is the formula? Minus b plus or minus root of b square minus 4ac divided by 2a. Using this formula you get 12 plus or minus, if you calculate that 144 minus 16, root of that is yielding 11.3 divided by 2. So you are getting lambda 1 as what? 11.65, and sorry about that, and lambda 2 as 0.35. You can observe they are real and they are greater than 0, right? So now let's look at the pivots. What was the matrix again? Let's write down 2, 4, 4, 10. So for this matrix, what is the row operation? R2 equals R2 minus 2R1. Correct. So for this matrix, after applying the row operation, you get 2, 4, 0, 10 minus 8 would be 2. You can observe pivots are 2 and 2, which are greater than 0. Let's calculate the determinant now. This is your first determinant. 2 is greater than 0. What about your 2 cross 2 determinant? That's 2, 4, 4, 10. You get 20 minus 16. 4 is greater than 0. This is your determinant. So positive definite matrix is a little clear, right? Shall we take one more example to solve this? We will consider a 3 cross 3 matrix now. Okay. Let us take a 3 cross 3 matrix. I will clear this so we can write comfortably. So consider a 3 cross 3 matrix with A as 3 minus 1, sorry about that, minus 1, 1, minus 1, 5, minus 1, 1, minus 1, 3. So what are the lambda values do you get after solving this? I want you all to try out. Okay, I will just tell you 2, 3 and 6. Okay, you can observe they're all positive. Now what about the pivots? Do row operations for this matrix, and pivots so pivots you get as 3, 14 by 3 and 54 by 21. I'm repeating again. I want you all to try this out, and if you have any doubts, get back to me. Okay, so the last way to confirm a symmetric matrix is positive definite is by using determinants, right? So determinants of this is 3, which is greater than 0. Determinant of 2 cross 2 is what? 15 minus 1, that's 14, is greater than 0. The last subdeterminant would be the 3 cross 3 matrix. Find out. You will get 36, which is again greater than 0. So this is 36. I will rewrite that part. Okay, so that's 36. So that concludes your positive definite matrix. But let's understand there's a fourth condition to check if a symmetric matrix is positive definite or not, and that's called minima. Okay, we can write down. The fourth condition is given as x transpose Ax has to be greater than 0, where x is any real vector and it is non-zero. The x is non-zero and it is a real vector. That is, it can have positive, negative, fractions, any value. But when you compute x transpose Ax, it always has to give greater than 0 value. Let's consider the previous example of 2 4 4 10 matrix. Okay, so your matrix A was 2 4 4 10. Now I will give a little space so we can accommodate our x transpose also. 2 4 4 10. We will accommodate our x transpose. So x1 x2, here it would be x1 x2. So when you solve for this, what equation do you get? You multiply all the three, you get 2x1 square plus 8x1 x2 plus 10 x2 square. Okay, let me write this clearly. Why is it not writing? X2 square. Okay, so this equation will have a minima. Okay, so geometrically, if you look at this, let me just draw an xy axis. If you geometrically try to draw these points, except when x1 x2 is 0, all other times it is positive. Okay, and it is circularly spreading. Why is it always positive? Because you can observe, let us take x1 as 1 and x2 as -1. If you substitute and solve, what do you get? 2 minus 8 plus 10. Minus 8 plus 10. So you can observe, since the these square terms are more compared to this x1 x2 terms, you will always end up with positive values. Now we will try to look at a non-positive definite matrix. We will modify that same matrix to get a non-positive definite matrix. Let's put a 3 over here. So this is not a positive definite matrix. Why? You can observe the determinant of 2 cross 2, that is 6 minus 16. So you are getting a negative determinant, right? Easy to identify. Let's try to write the equation now. For this you will get 2x1 square plus 8x1 x2 plus 3x2 square. Now again let's try substituting 1 and minus 1. What do you essentially get? 2 minus 8 plus 3, which is less than 0. So if you represent the x transpose A, sorry, x transpose AX equation geometrically, you get something sort of a saddle. That is, at some point it is maximum, for some equation it is the minimum, right? So this is the last condition to say if your symmetric matrix, oops, sorry about that, if your positive definite matrix or not, a symmetric matrix is positive definite matrix or not. That is, this is your fourth condition. The first three conditions are simple, and this is called as minima condition. Okay, that covers the topics for today. Thank you.